Alright, so we're going to get into the law of sines today, tomorrow the law of cosines. And this is in chapter 7, so kind of diverting from where we've been in chapter 5 with trigonometry. But when we're talking about using these other ideas of law of sines and law of cosines, which you should have seen in the past, but if not, we're going to kind of re-go over them here. When do we use sine, cosine, and tangent? And so what have we been doing in the past week and a half or so is we've been using sine, cosine, tangent when we're dealing with right triangles. Our definitions of what each of these ratios represents are based off of working in right triangles, adjacent side, opposite side, hypotenuse. So where the law of sines and law of cosines comes in is what about all the other types of triangles? How do we deal with obtuse triangles, acute triangles, things of that nature that the right triangle trigonometry doesn't really fit with. And I'm actually going to show you how to quickly come up with the law of sines. What you need is the end product here, not necessarily the beginning, but the idea here, and you can see the picture, we have a triangle that's, in this case, it's any size. The side lengths, and the important thing to notice here, side A is across from angle A, side B across from angle B, side C across from angle C. So the labeling of triangles is important when you're talking about using this law of sines and law of cosines, because keeping the placement straight is important. But you see, we have any old triangle here. Those side lengths A, B, and C can be whatever you want. And the idea in developing this formula is you take this temporary line we're going to use, and this is called an altitude that goes through the vertex and is perpendicular to side C here. And we're just giving it some arbitrary length k, however long it happens to be. The important thing is it's at a right angle. We can also label, not that we'll need it for this particular law, but we'll label our two sides, so we'll break C into these two pieces, so however long x is, and then whatever is left over as the other length. So the idea is we want to look at law of sines. We're going to use sine. And what you want to think about is, okay, how would I write an expression? Now I have two right triangles. How would I write an expression involving the sine of A, angle A, and the sine of angle B? So the sine of angle A, you say to yourself, sine relates the opposite side over the hypotenuse. So for angle A, the opposite side is K, and the hypotenuse would be B. So we're going to write our first expression, sine of angle A is K over B. Same idea. What about, we're going to do the sine of angle B. Sine of angle B is opposite side is K, hypotenuse is A, so sine of angle B is K over A. From here, all we have is a little bit of algebra. So we're going to, in both cases, for both equations, solve for K, get K alone. So in the first equation, take times B on both sides to cancel out the B's, and we get K is equal to B times sine of A. In the second equation, we're going to multiply by A on both sides to get K alone, so the A's cancel out, and we get K is equal to A times sine of B. Now this algebra is about manipulating the equations, changing them, and combining them. So we have K in both equations here. So that means I can substitute in, instead of having K written there, I can substitute in B times sine of A. So our equation becomes, and if this is going a little bit too fast for you, don't worry because we're about to get to the final product here. The idea is now I have an equation involving sine, and notice I have all the original pieces from, or what the equation involves is the original pieces from my original triangle. Side lengths A and B, and angles A and B. Doesn't say anything about opposite, hypotenuse, anything like that. It's just based off of those side lengths. So that's the idea. And when we write we wrote the law of sines. We don't normally write it this way. We divide both sides of the equation by b. We divide both sides of the equation by a. And we rewrite it in this kind of nicer form. Sine of the angle over the side opposite equal to sine of another angle over the side opposite. And we throw the sine c. We don't necessarily use all three of these sets of ratios to solve when we're talking about law of sines. But we throw the sine c in there because if we had arranged things differently, it doesn't mean you can't use side c and angle c. It's just kind of the convention of writing it. So this is the way the law of sines is developed and proved. And so here you have it written out. But again, the most important thing is the angles here, when we're talking about the law of sines and law of cosines, angles and side across from it are corresponding to each other. So when should we use the law of sines? Well, this actually works for any triangle as far as different angles, works for all triangle types, meaning acute, obtuse, and right. It actually does work on right triangles, so if you wanted to modify this to right triangles, that's fine. But the important thing is you need to have information about angles and the sides across for them. So on Wednesday and Friday, you'll kind of see more and sides across from them. On Wednesday and Friday, when we do law of cosines, you'll see the different places where law of sines would work better, some places like law of cosines would work better. So we have two examples we're going to run through, the two different cases you could possibly run into as far as working with law of sines. So in our first example here, notice we have a triangle that is clearly not a 90-degree triangle. So if I want to find that third angle, take away from 180 degrees, that third angle would be 109 degrees. So definitely not a right triangle. We have an obtuse triangle here. It says we want to find the length of FG. So I'm going to mark that with an X so that I remember what I'm actually looking for here. So this is a case for law of sines. If you don't have a right triangle, you can't just say opposite, hypotenuse, adjacent. All of those terms don't apply if you don't have a right triangle. So we need to use the law of sines. So sine of an angle over its opposite side equals sine of a different angle over the opposite side. So what you want to do is pair up angles and sides. So I have, for instance, angle F here is going to pair up with a side opposite it. So I'm going to put sine of angle F over, and the side opposite it would be GH. The angle opens up to this side. Also, I can write the sine of angle H, and which side does it go with? It goes and opens up to X. So the idea, oops, sorry, I've got to put FG. The idea here is you want to find three pieces of information when you're writing your law of sines. So the three pieces of information I have are, I have angle F is 39 degrees. I have GH is 40. I have angle H is 32. And the piece of information I don't have that I want to solve for is this X value. So kind of like what I showed you guys at solving sine, cosine, and tangent in general, we want to use cross multiplication to solve for the missing piece. So we set up sine of the angle over the opposite side, two different angles, two different sides, and now all we have to do is cross multiply. So 40, and I'm going to wait to type all this in until the end. 40 times sine of 32 degrees on one side, and x times sine of 39 degrees on the other side. So how do we get x alone? Well, divide by sine of 39 degrees on both sides. Making sure you're in degree mode. You type this in, you should get that x is equal to And because it's a side length, I'm going to round it to hundredths. I'm getting 33.68. No units on that. So FG is equal to 33.68. Law of sines becomes pretty natural once you practice it a few times. It becomes not too difficult at all. So there's the setup where you're looking for a side, kind of like when we do sine, cosine, and tangent in general. And then there's the setup where you're looking for an angle. So if we want to find the measure of angle Q, we want to do that same. So we have, there's our variable, what we're looking for. We have that same general setup. You want to match up angle with a side across from it, angle with a side across from it. So we're going to set up law of sines with sine of angle P over RQ, because that's the side opposite it, and sine of angle Q over PR. So now we just need to fill in what we know and what we don't, as far as variables. So angle P is 51 degrees, and RQ is 8. Sine, and we don't know angle Q, so we're going to throw in our variable x here. And PR is 6. So now, again, how do we solve when we're the only sine, cosine, tangent? We're going to try and cross multiply. So 6 times sine of 51 degrees equals 8 times sine of, and we don't know what that angle is, so we're going to leave it as x. So how do we solve from here? And this is where you got to use a little bit of what we were talking about yesterday as far as solving for the angle. We're going to use the inverse sign. We're going to use those inverse functions. But before we can use the inverse sign, we got to get x alone by taking away piece by piece. So first piece we want to take away is dividing by that 8. So 6 times sine of 51 degrees divided by 8 equals sine of x. And now we want to remove that sine function. To remove the sine, we do the opposite, which is sine inverse. So on both sides, and this is the part where you got to watch what you're typing in. You want to take the inverse sine, and that entire 6 times sine of 51 divided by 8 is what needs to go into the parentheses. Make sure you type this in and try this right now, following along. And if it needs to, pause the video to follow along and type things in. You should get an x value of 35.65 degrees. We said we were going to round to the nearest degree, so 36 degrees even. This missing angle here is 36 degrees. So solving for the angle is a little bit more complicated, but still that same basic setup. And that's why you need to practice it so you get used to the idea of solving that missing angle. So if we wanted to here, we could find angle R by doing 180 minus 51 minus 36. Still the triangle has to equal to 180 degrees, so that's not changed. So this would be 93 degrees. So law of sines, you've seen 2 examples, and now you're going to get to practice some of these kind of setups, realizing they can be used with right triangles, they can be used with acute or obtuse triangles as well. But can we use law of sines for every triangle and every angle? No, that's why we have various trigonometric setups, including law of cosines, which you'll see tomorrow. If you look at the triangle that's displayed here, a big reason you can't use law of sines, well, think about your setups. Sine of an angle over its opposite side, sine of another angle over the side that's opposite it, and sine of an angle with a side that's opposite it. The problem is sometimes some triangles you may not have enough information to solve. So we don't have a set of an angle and a side across from it. And there are other issues that come along that we'll talk about later where obtuse angles are an issue as well. But you're going to practice that basic setup.